Hey, my friend. Tonight we're going to take a slow and gentle journey, not across the stars, but through something even stranger, time itself. Time feels so ordinary that we rarely stop to question it. It moves quietly in the background of our lives, marked by the ticking of clocks, the turning of days, and the slow rhythm of our own breathing. Morning becomes afternoon, afternoon becomes evening, and without thinking much about it, we assume time is flowing the same way for everyone, everywhere. But the universe tells a very different story. As we explored in another Valoran episode about the mysterious nature of spacetime and black holes, the cosmos has a way of turning our everyday assumptions upside down. And time may be the most surprising example of all. Because according to modern physics, time is not the same everywhere in the universe. In some places it moves a little slower. In other places it moves a little faster. And under the most extreme conditions, it can stretch so dramatically that a single hour for one observer might correspond to years for another. This isn't science fiction. It is a quiet but profound discovery made by physicists over the last century. A discovery that began when scientists started asking a simple question. What is time, really? For thousands of years, humans imagined time as a steady cosmic river flowing the same way for everything in existence. Even Isaac Newton believed time was absolute, a universal clock ticking identically across the entire universe. But early in the 20th century, a young physicist named Albert Einstein began to realize something extraordinary. Time was not a universal river at all. Instead, it was woven into the very structure of the universe itself. And once we begin to see time this way, an entirely new picture of reality begins to emerge. One where every person, every planet, and every star follows its own quiet path through time. Before we drift deeper into this strange cosmic story, take a moment to settle in. If you enjoy calm explorations of the universe like this, consider subscribing to Valoran's Sleepy Space Mysteries, leaving a like, and perhaps joining the channel if you'd like to support more journeys like this one. And just out of curiosity, where in the world are you watching from tonight? For most of human history, the nature of time seemed perfectly obvious. Seconds passed, minutes accumulated, days turned into years, and everything in the universe appeared to move forward together along the same invisible timeline. It was such an intuitive idea that few people felt the need to question it deeply. Time, it seemed, was simply the stage upon which the events of the universe unfolded. The planets moved, objects fell, people lived their lives, and through it all time ticked steadily in the background like a perfectly reliable cosmic clock. This picture reached its most powerful expression in the work of Isaac Newton. In the late 17th century, Newton developed a framework of physics that explained the motion of objects with remarkable accuracy. Apples fell from trees, cannons fired their projectiles, and planets traced graceful paths around the sun, all following mathematical laws that seemed beautifully precise. Within this framework, time was treated as something absolute. Newton described it as flowing uniformly everywhere in the universe, independent of anything else that might be happening. According to this view, the interval between two events was the same for everyone, no matter where they were or how they were moving. For centuries, this idea worked extraordinarily well. Engineers built machines, astronomers predicted planetary motions, and scientists described countless physical processes using Newton's assumptions about time. It seemed that humanity had finally uncovered the fundamental rhythm of the cosmos. But toward the end of the 19th century, subtle cracks began to appear in this seemingly solid foundation. The trouble began with light. Physicists had learned that light behaved like a wave, similar in some ways to waves traveling across water or vibrations moving through the air as sound. Waves usually require a medium, something to move through. Ocean waves move through water, sound waves travel through air, and so it seemed reasonable to assume that light must also travel through some invisible substance filling all of space. Scientists called this mysterious medium the ether. According to the prevailing theory of the time, the entire universe was filled with this ether, and light waves propagated through it as they traveled across space. If this were true, then Earth would be constantly moving through this cosmic ocean as it orbited the Sun. And if Earth were moving through the ether, then the speed of light should appear slightly different depending on the direction you measured it. Imagine riding a bicycle into a strong wind. The air seems to rush toward you faster than when the wind is behind you. Physicists expected something similar to happen with light if the Earth were moving through the ether. In 1887, two scientists named Albert Michelson and Edward Morley designed one of the most precise experiments ever attempted at the time. Their goal was simple: detect Earth's motion through the ether by measuring tiny differences in the speed of light traveling in different directions. The experiment was extraordinarily delicate. Mirrors and beams of light were arranged with incredible precision so that even the slightest difference in light speed could be detected. And yet, when the measurements were completed, something astonishing happened. They found nothing. No matter how carefully they performed the experiment, no matter how many times they repeated it, the speed of light appeared to be exactly the same in every direction. It did not matter how Earth was moving. It did not matter which direction the light traveled. The result remained stubbornly unchanged. For many physicists, this outcome was deeply unsettling. It suggested that something about the existing understanding of space and time was incomplete. Some scientists attempted to rescue the ether theory with complicated explanations, suggesting that objects might physically contract when moving through the ether or that measuring instruments somehow changed their size. But these ideas felt increasingly artificial, like patches placed on a theory that was beginning to unravel. And then, in 1905, a young patent clerk working in Switzerland proposed a radically different way of looking at the problem. His name was Albert Einstein. Instead of trying to preserve the old assumptions about space and time, Einstein made a bold decision. He began with a simple idea that would quietly overturn centuries of intuition. What if the strange result of the Michelson-Morley experiment was not a problem to fix, but a clue about how the universe truly works? Einstein's approach to the puzzle of light was surprisingly simple, yet its consequences were enormous. Rather than inventing complicated mechanisms to explain why the ether could not be detected, he proposed that perhaps the ether did not exist at all. Instead, he suggested that the laws of physics themselves might be structured in a deeper way than anyone had realized. His entire theory of special relativity began with two deceptively modest principles. The first was that the laws of physics are the same for all observers who move at constant speeds relative to one another. In other words, there is no special or privileged state of motion in the universe. Whether you are standing still on Earth, riding on a train, or drifting through deep space at a steady speed, the basic rules governing nature remain identical. The second principle was even more surprising. Einstein proposed that the speed of light in empty space is always the same for every observer, regardless of how fast they are moving or how fast the source of light is moving. At first glance, this statement might not seem particularly dramatic, but when physicists began to think carefully about its implications, they realized something astonishing. In everyday experience, speeds normally add together. If you are walking forward on a moving train and you throw a ball ahead of you, someone standing on the ground will measure the ball's speed as the speed of the train plus the speed of your throw. This simple addition of velocities works perfectly well for most things we encounter in daily life. But light refuses to behave this way. If a flashlight is turned on inside a moving spacecraft, both the astronaut holding the flashlight and an observer watching the spacecraft from Earth will measure the light leaving the flashlight at exactly the same speed. Somehow the universe preserves this speed no matter what the circumstances are. This creates a puzzle. If the speed of light never changes, then something else must adjust itself to compensate. Einstein realized that the only quantities flexible enough to accommodate this strange rule are space and time themselves. In order for every observer to measure the same speed of light, the distances they measure and the time intervals they experience must shift depending on how they are moving relative to one another. Space can stretch or compress. Time can slow down or speed up. Together they rearrange themselves so that the speed of light remains constant. One of the most fascinating consequences of this idea is the relativity of simultaneity. Imagine a long train moving at high speed along a straight track. At the exact moment the center of the train passes a platform observer, two flashes of lightning strike the front and the back of the train simultaneously from the perspective of someone standing on the platform. The light from both strikes travels toward the center of the train. Because the platform observer is exactly halfway between the strikes, the light reaches them at the same moment, confirming that the strikes occurred at the same time. But now consider the passenger standing in the middle of the train. While the light is traveling toward them, the train itself is moving forward. This means the passenger is moving toward the light coming from the front strike and moving away from the light coming from the rear strike. As a result, the light from the front reaches them slightly sooner than the light from the back. From the passenger's perspective, the strike at the front happened before the strike at the rear. Both observers are correct within their own frames of reference. The disagreement is not due to faulty measurement or misunderstanding. Instead, it reveals that the concept of two distant events happening at the same time depends on the observer's motion. What counts as now for one observer may not be now for another. This realization alone was enough to overturn centuries of assumptions about time being universal. The universe does not share a single synchronized present moment. Each observer carries their own slice of time through spacetime, defined by their motion. Once simultaneity becomes relative, other consequences quickly follow. If observers moving relative to one another disagree about whether two events happen at the same time, they must also disagree about the amount of time that passes between events. This leads to the phenomenon known as time dilation. A moving clock, when observed from another frame of motion, will appear to tick more slowly. The effect is not caused by mechanical imperfections in the clock or by any external interference. It is a fundamental feature of how time behaves in the structure of spacetime itself. At everyday speeds, the effect is extremely small, far too tiny for our senses to notice. But as an object's speed approaches the speed of light, the difference becomes more dramatic. Time for the moving observer begins to stretch relative to someone who remains at rest. What seemed like an abstract idea soon turned out to be a measurable property of the universe, one that experiments would later confirm with astonishing precision. And with that realization, the comfortable idea of a single universal clock quietly disappeared from physics forever. Once physicists began to accept that time itself could stretch and contract depending on motion, the implications became both strange and fascinating. One of the simplest ways to imagine time dilation is to think about a clock traveling aboard a very fast spacecraft. To the astronaut inside the ship, everything appears completely normal. Their clock ticks steadily. Their heartbeat remains regular. Conversations unfold at the usual pace. Nothing in their immediate surroundings suggests that anything unusual is happening with time. But an observer watching the spacecraft pass by at enormous speed would see something different. From their perspective, the astronaut's clock appears to tick more slowly. Each second aboard the ship takes slightly longer to pass compared to seconds on Earth. The faster the spacecraft travels, the more noticeable this difference becomes. If the spacecraft could approach extremely close to the speed of light, the slowing of time would become dramatic. This effect may sound like a strange illusion caused by the way we observe motion, but it is not an illusion at all. It is a measurable physical difference. If the astronaut eventually returned to Earth and compared their clock with one that had remained on the ground, the two clocks would no longer agree. The traveling clock would show that less time had passed. This surprising consequence is sometimes illustrated by the famous twin scenario. Imagine two identical twins. One stays on Earth while the other boards a spacecraft capable of traveling at extremely high speed. The traveling twin journeys across space for what feels like a few years before returning home. When they reunite, something remarkable has happened. The twin who remained on Earth has aged more than the one who traveled. From the traveler's point of view, the trip may have lasted only a handful of years, while decades may have passed on Earth. The idea that motion through space can slow the passage of time might seem like the kind of concept that belongs purely to science fiction stories. Yet nature provides us with countless examples that confirm it. One of the most elegant confirmations comes from tiny particles created high above Earth in the upper atmosphere. These particles are called muons. They form when cosmic rays, energetic particles arriving from outer space, collide with atoms in Earth's atmosphere. Muons are unstable and decay quickly, surviving for only a tiny fraction of a second when at rest. If muons behaved according to Newton's classical understanding of time, they would decay long before reaching the surface of Earth. They simply would not live long enough to travel the distance from the upper atmosphere to the ground. And yet detectors placed at Earth's surface routinely observe large numbers of these particles arriving from above. The explanation lies in the fact that muons travel at speeds extremely close to the speed of light. Because they are moving so quickly, time for them slows down relative to observers on Earth. From the muon's perspective, its internal clock still runs normally. But from our perspective on the ground, its lifetime is stretched. This time dilation allows the particle to survive long enough to reach detectors at the surface. Laboratory experiments have confirmed the same effect in controlled conditions. In particle accelerators, scientists can create beams of particles traveling at tremendous speeds. These particles live noticeably longer than identical particles that remain at rest. The faster the particles move, the longer they survive before decaying. Every measurement matches Einstein's predictions with astonishing precision. Even objects much larger than subatomic particles reveal the same behavior when measured with extremely accurate instruments. In the 20th century, physicists performed experiments using atomic clocks placed aboard high-speed aircraft. Identical clocks were synchronized on the ground and then flown around the world on commercial jets. When the aircraft returned and the clocks were compared, a tiny difference appeared. The clocks that had been moving through the air showed slightly less elapsed time than those that had remained on Earth. The difference was incredibly small, only fractions of a microsecond, but it was exactly what Einstein's theory predicted. These experiments demonstrated that time dilation is not merely a mathematical curiosity. It is a real physical phenomenon that affects any object moving at high speed. At the gentle speeds of everyday life, walking, driving, or even flying in an airplane, the differences in time are far too small for us to notice. But they are always there, quietly shaping the rhythm of the universe. Every moving object experiences its own slightly unique passage of time, determined by its motion through spacetime. And as physicists continued exploring this strange new understanding of reality, they soon discovered that motion was not the only thing capable of bending time. Gravity itself would turn out to have an equally powerful influence. As physicists grew more confident that motion could alter the passage of time, another question slowly began to emerge. If speed alone could stretch time, what about gravity? After all, gravity governs the motion of planets, stars, and galaxies. It shapes the large-scale structure of the universe. Could it also influence time itself? At first glance, the connection might seem unlikely. In Newton's picture of the universe, gravity was simply a force that pulled objects toward one another. Apples fell to the ground, the moon orbited Earth, and planets circled the sun because gravity acted between masses across empty space. Time in this framework remained untouched by gravity. Seconds passed at the same rate everywhere in the cosmos. But Einstein suspected that this picture was incomplete. While developing his ideas about motion and relativity, Einstein noticed something curious about acceleration and gravity. If you stand inside a closed elevator and feel yourself pressed against the floor, there are two possible explanations. Perhaps the elevator is resting on Earth's surface and gravity is pulling you downward. Or perhaps the elevator is floating far out in space, but its engines are accelerating upward. In both cases, the sensation you feel would be identical. Without looking outside, you would not be able to tell the difference. This simple observation became one of the most profound insights in modern physics. Einstein realized that gravity and acceleration are deeply connected. The effects produced by gravity can be mimicked by acceleration, and the effects of acceleration can resemble those of gravity. This idea became known as the equivalence principle. Once this connection was understood, the consequences began to unfold in remarkable ways. If acceleration could affect the passage of time in the same way motion does, and if gravity is equivalent to acceleration, then gravity must also influence time. Einstein spent years developing the mathematics needed to describe this new vision of the universe. Finally, in 1915, he presented the theory that would become known as general relativity. In this theory, gravity is no longer described as a mysterious force pulling objects together. Instead, it emerges from the geometry of spacetime itself. Imagine spacetime as a vast, flexible landscape. When a massive object like a planet or star exists within this landscape, it causes the surrounding spacetime to curve. Objects moving nearby follow paths through this curved geometry. From our everyday perspective, these curved paths appear as the familiar effects of gravity. But the curvature does not only affect the motion of objects through space. It also affects the passage of time. In regions where gravity is stronger, time moves more slowly relative to regions where gravity is weaker. This effect is known as gravitational time dilation. It means that two identical clocks placed in different gravitational environments will not remain synchronized. One clock placed deep within a gravitational field will tick slightly more slowly than a clock located farther away from that gravitational influence. On Earth, the difference is extremely small, far too small for human senses to detect. But with precise instruments, scientists have measured it many times. Experiments using atomic clocks have demonstrated that a clock located at sea level ticks slightly more slowly than one placed on a mountain peak. The difference is tiny, but perfectly consistent with the predictions of general relativity. The same principle becomes more noticeable in space. Satellites orbiting Earth experience weaker gravity than objects on the surface. Because of this, their clocks run slightly faster than clocks on the ground. At the same time, the satellites are also moving quickly, which causes a smaller time dilation effect that slows their clocks slightly. The two effects combine in a fascinating way. The reduced gravity speeds up satellite clocks, while their motion slows them down. The net result is that the clocks on navigation satellites tick slightly faster than those on Earth. If these differences were ignored, modern navigation systems would fail quickly. The global positioning system relies on incredibly precise timing signals transmitted from satellites. Even tiny differences in clock rates would accumulate into massive navigation errors. Engineers must therefore include corrections for both special relativity and general relativity in order to keep the system accurate. Every time a smartphone calculates its location, it is quietly relying on Einstein's understanding of how gravity and motion reshape time. This realization reveals something deeply beautiful about the nature of the universe. Time is not a rigid background against which events unfold. It is part of the structure of reality itself, bending and stretching alongside space. Motion can change the pace of time. Gravity can reshape it. And as scientists began exploring the most extreme environments in the cosmos, they discovered that these effects could become far more dramatic than anything experienced near Earth. Near certain cosmic objects, time does not merely slow by a tiny fraction. It can slow so dramatically that entire years elsewhere in the universe may pass in the span of only hours. And those extraordinary places exist in the darkest regions of the cosmos. By the early 20th century, Einstein's ideas had completely transformed the scientific understanding of time. What once seemed like a universal background ticking steadily for the entire cosmos was now revealed to be something far more flexible. Time could stretch, slow, and diverge depending on motion and gravity. Each observer carried their own clock, and the universe no longer obeyed a single synchronized timeline. Yet the most fascinating aspect of relativity is not simply that time can change. It is that these changes are woven directly into the structure of spacetime itself. Motion through space and motion through time are not separate processes. They are deeply connected aspects of the same four-dimensional geometry. One helpful way to imagine this is to picture every object in the universe following a path through spacetime called a world line. From a tiny grain of dust to an entire galaxy, everything traces its own trajectory through this cosmic landscape. These world lines describe not only where something moves in space, but also how it moves through time. In Einstein's framework, all objects move through spacetime at the same overall rate. What changes is how that motion is divided between space and time. When an object is at rest relative to you, most of its motion through spacetime is directed along the time dimension. It is moving steadily forward in time while remaining relatively fixed in space. But when that object begins moving quickly through space, some of its motion through spacetime shifts away from the time direction and into spatial motion. The result is that less motion remains along the time dimension. And when less motion occurs through time, time itself appears to pass more slowly for that object relative to others. This idea may sound abstract at first, but it provides a beautiful way of understanding why time dilation occurs. Speeding up through space effectively trades some of your motion through time. The faster you travel through space, the slower you move through time compared with someone who remains stationary. At everyday speeds, the exchange is tiny, so small that it escapes our notice completely. A person walking down the street experiences time almost identically to someone sitting on a bench. Even a jet airplane traveling across the sky moves far too slowly for the effect to matter in daily life. But the closer an object moves toward the speed of light, the more dramatic the trade-off becomes. At 90% of light speed, time for the traveler slows significantly relative to an outside observer. At 99%, the difference becomes even more pronounced. The traveler's personal experience of time continues normally, yet the rest of the universe ages more rapidly in comparison. This remarkable property of the universe has inspired generations of scientists and science fiction writers alike. It suggests that high-speed travel could act as a kind of natural time machine, carrying travelers far into the future relative to those they left behind. A journey lasting only a few years aboard a near-light-speed spacecraft might correspond to decades or centuries passing elsewhere. Although such voyages remain far beyond our current technological capabilities, the physics itself is well established. Relativity does not forbid such journeys. In fact, it quietly predicts them. But motion is only half of the story. As we have already begun to glimpse, gravity can bend time just as profoundly as speed can. Near massive objects, the fabric of space-time curves deeply, and within that curvature time itself slows. In gentle gravitational fields like Earth's, the effect is tiny. But as gravity grows stronger, the slowing of time becomes more dramatic. This leads us towards some of the most extraordinary environments in the universe. There exist places where gravity is so intense that time nearly grinds to a halt compared with the rest of the cosmos. These places are the domains of collapsed stars, neutron stars, and the most mysterious objects of all, black holes. Near these objects, the quiet flexibility of time becomes something far more extreme. Seconds stretch, clocks diverge dramatically, and the flow of time itself begins to behave in ways that would seem almost impossible if not for the precise predictions of relativity. Understanding how gravity reshapes time will take us deeper into the geometry of space-time than ever before. It will lead us into regions where the universe reveals just how far our everyday intuition can be stretched. And as we move closer to those extreme environments, we will discover that time is not merely something we measure. It is something the universe itself bends. When Einstein first realized that gravity could influence the flow of time, it opened a doorway into one of the most surprising aspects of the universe. Until that moment, gravity had always been thought of as a simple force, something that pulled objects together across empty space. Newton's equations had described this pull with extraordinary accuracy for centuries. Planets orbited the sun exactly as predicted, comets returned on schedule, and falling objects obeyed the familiar acceleration toward the ground. Yet Newton's gravity operated within a universe where time itself remained untouched. Seconds ticked at the same rate everywhere, unaffected by mass, motion, or distance. Einstein's insight changed this picture completely. Instead of treating gravity as a force acting across space, he began to think of it as a property of spacetime itself. Massive objects such as planets, stars, and galaxies do not simply pull on other objects. They reshape the very geometry of the universe around them. Space and time form a single interconnected fabric, and when matter exists within that fabric, it causes the geometry to curve. A useful way to imagine this is to picture spacetime as a vast flexible surface. If you place a heavy object on this surface, it creates a depression around it. Smaller objects moving nearby follow paths along the curved surface. From our perspective, those curved paths appear as gravitational attraction. The objects are not being pulled by a mysterious force in the traditional sense. Instead, they are simply moving along the natural geometry created by the presence of mass. But the curvature of spacetime does more than guide the motion of objects through space. It also changes the rate at which time passes. In regions where spacetime is more deeply curved by gravity, time flows more slowly compared to regions where the curvature is weaker. This means that clocks placed in stronger gravitational fields tick at a slower pace relative to clocks located farther away from massive objects. This effect is called gravitational time dilation. To someone experiencing the stronger gravity directly, nothing unusual seems to happen. Their clock ticks normally. Their thoughts, movements, and biological rhythms all proceed at the familiar pace of daily life. But when compared with a clock located in weaker gravity, a difference slowly emerges. The clock deeper in the gravitational field falls behind. On Earth, the effect is extremely small, yet modern instruments are sensitive enough to measure it. Atomic clocks are so precise that they can detect differences in time caused by even tiny changes in gravitational strength. Experiments have shown that a clock positioned closer to Earth's surface runs slightly more slowly than an identical clock placed higher above the ground. The difference might only amount to tiny fractions of a second over long periods, but it is real and consistent with the predictions of general relativity. This means that time at the base of a mountain passes ever so slightly slower than time at the summit. A person living by the ocean ages very slightly slower than someone living high in the mountains. The difference is far too small to notice in everyday life, but it reveals that gravity quietly reshapes the rhythm of time all around us. As we move beyond Earth, these effects become easier to observe. Satellites orbiting our planet travel through regions where gravity is weaker than it is at the surface. Because of this, time for the satellites runs slightly faster. Their clocks gradually drift ahead of clocks on Earth. Engineers must carefully correct for these differences in order for satellite navigation systems to function properly. Without accounting for gravitational time dilation, the timing signals used for global navigation would drift out of alignment, producing enormous errors in position calculations. In this quiet way, Einstein's understanding of gravity has become part of everyday life. Each time a navigation system determines your location, it relies on corrections based on the idea that gravity bends time. But Earth's gravity is relatively gentle compared with the forces found elsewhere in the universe. Our planet is only a small mass compared to the enormous stars scattered across the cosmos. Around these larger objects, the curvature of spacetime grows stronger, and the slowing of time becomes more pronounced. If we travel outward in imagination to the most extreme objects in the universe, we begin to encounter places where the flow of time diverges dramatically from what we experience on Earth. And among these objects, none reshape time more profoundly than the collapsed remnants of massive stars. As we move beyond the relatively gentle gravity of Earth and begin exploring the more extreme objects in the cosmos, the influence of gravity on time becomes far more dramatic. Our planet, massive as it seems to us, is actually a modest object on the cosmic scale. There are stars thousands of times larger, and collapsed stellar remnants where enormous mass is compressed into astonishingly small regions of space. In these environments, the curvature of spacetime becomes far steeper, and with it, the distortion of time grows stronger. One of the first places where this effect becomes truly significant is around neutron stars. A neutron star forms when a massive star reaches the end of its life and collapses under its own gravity during a supernova explosion. The outer layers of the star are blasted away into space, while the core is crushed into an incredibly dense sphere. What remains is an object with a mass often greater than that of our Sun, but compressed into a sphere only about 20 kilometers across. The density of such a star is almost beyond imagination. A single teaspoon of neutron star material would weigh billions of tons on Earth. Gravity at the surface of a neutron star is therefore immense. The curvature of spacetime surrounding it is far stronger than anything experienced in our solar system. Because of this intense gravitational field, time on the surface of a neutron star flows noticeably slower compared with time far away from the star. If an observer could somehow hover safely above such an object and watch a clock resting on its surface, the ticking would appear slower and slower as the gravitational field deepened. To the observer far away, every second near the neutron star would stretch slightly longer. Yet for anyone standing on the neutron star itself, assuming such a thing were possible, time would feel completely normal. Their own clock would tick steadily. Their heartbeat would follow its usual rhythm. Only when their clock was compared with one located far away would the difference become clear. This strange relationship between gravity and time highlights one of the deepest features of relativity. The rate at which time passes depends on the environment in which the observer exists. There is no universal clock that governs the entire universe. Instead, every region of space carries its own pace of time. Neutron stars already represent an extreme example of this principle, but they are not the most dramatic places where gravity bends time. Even more remarkable environments exist where gravity becomes so intense that spacetime itself begins to twist into extraordinary shapes. These environments are found around black holes. Black holes are formed when the core of a massive star collapses so completely that nothing can stop its inward fall. Gravity overwhelms every known force that could resist it. The matter compresses into an incredibly small region, creating a gravitational field of astonishing strength. Surrounding this collapsed core is a boundary known as the event horizon. This boundary marks the point where the escape velocity equals the speed of light. Once anything crosses this threshold, not even light can escape the pull of the black hole. The space-time near this boundary is curved so steeply that time behaves in extraordinary ways. Imagine placing a clock near the edge of a black hole's event horizon while observing it from a safe distance far away. As the clock approaches the black hole, you would begin to notice something remarkable. The ticking of the clock would appear to slow. Each second would take slightly longer to arrive than the one before. As the clock moves closer and closer to the event horizon, the effect grows stronger. The ticking slows more and more from the perspective of the distant observer. Light emitted by the clock becomes stretched toward longer wavelengths, a phenomenon known as gravitational redshift. Eventually, the clock would appear to tick so slowly that it seems almost frozen in time. From the distant observer's perspective, the clock never quite reaches the event horizon. Its final moments stretch endlessly into the future. The closer it approaches the horizon, the slower its time appears to pass. But this strange observation hides an equally surprising truth. From the viewpoint of the clock itself, Nothing unusual happens to time at all. The clock continues to tick normally. The observer falling toward the black hole experiences their own time passing as usual, unaware that the outside universe appears to be racing ahead relative to them. This difference in perspective is one of the most fascinating consequences of relativity. Time is not a single universal river flowing everywhere at the same pace. It is deeply tied to the geometry of spacetime and to the position and motion of each observer. And nowhere is this more dramatically revealed than near the edge of a black hole. The strange behavior of time near a black hole becomes even more fascinating when we imagine the experience of someone actually falling toward it. From a distant observer's perspective, the approach toward the event horizon appears to slow more and more. The falling object seems to move in slow motion, its signals stretched and dimmed as gravity distorts the light climbing outward. Eventually, the image fades almost completely, leaving behind the impression that the object has frozen in place at the edge of the black hole. But for the traveler falling inward, the story unfolds very differently. If an astronaut could approach a sufficiently large black hole, one with a mass millions of times greater than our Sun, they might cross the event horizon without immediately noticing anything dramatic. The region of space just outside the horizon of such a massive black hole can actually be relatively calm compared with the violent environments surrounding smaller ones. The astronaut's spacecraft would continue to fall inward smoothly, guided by the curved geometry of spacetime. Inside the spacecraft, everything would feel normal. Clocks would tick at their usual pace. Conversations would proceed naturally. Instruments would behave exactly as expected. From the astronaut's perspective, time would continue flowing in the same steady rhythm they had always experienced. Yet outside the spacecraft, something extraordinary would be happening. As the astronaut moved deeper into the gravitational well, the difference between their personal time and the time experienced far away in the universe would grow larger and larger. Events occurring in distant regions of space would appear to unfold more rapidly relative to the astronaut's own clock. In principle, if the astronaut could somehow hover extremely close to the event horizon and look outward, they might witness a remarkable spectacle. The distant universe could appear to evolve at an accelerated pace. Stars might shift positions in the sky. Entire generations of civilizations might rise and fade while only hours or days passed for the observer near the black hole. This possibility reveals one of the most dramatic consequences of gravitational time dilation. In extreme gravitational environments, the difference between local time and distant time can grow enormous. The deeper the gravitational well, the slower time flows relative to the rest of the cosmos. This effect has inspired many imaginative scenarios in both scientific discussions and works of fiction. One famous example appears in the film Interstellar, where astronauts visit a planet orbiting close to a massive black hole. In the story, the gravitational field is so strong that 1 hour on the planet corresponds to 7 years for observers far away. While the exact numbers in such scenarios depend on specific conditions, the underlying physics is firmly rooted in Einstein's theory. Gravity really can stretch time by enormous factors when the gravitational field becomes strong enough. Even though humans are unlikely to visit such environments anytime soon, Astronomers observe indirect evidence of these effects in the universe. Near many black holes, enormous disks of hot gas spiral inward, glowing brightly as they accelerate through the curved spacetime surrounding the hole. The light emitted by this gas often appears shifted toward longer wavelengths, a signal that gravity is affecting both the energy of the light and the passage of time near the source. By studying these signals, scientists can estimate the mass and rotation of distant black holes. The warping of time leaves measurable fingerprints in the radiation escaping from these extreme regions. But perhaps the most profound realization is not simply that time slows near black holes. It is that time itself is woven into the same fabric as space. The geometry that shapes the motion of planets and stars also shapes the rhythm of seconds and minutes. In everyday life, we rarely notice this flexibility. The differences between clocks on Earth are tiny. Two people standing side by side experience nearly identical flows of time. Yet, even then, the universe is quietly maintaining its intricate structure. The gravitational pull of Earth is slightly slowing our clocks compared with those farther away in space. Every mountain peak, every orbiting satellite, every star in the galaxy occupies its own subtle position in the cosmic web of time. And once we begin to see the universe this way, another remarkable idea begins to emerge. If gravity and motion can reshape the passage of time so dramatically, then perhaps the universe itself contains natural pathways through time. Paths that allow travelers to experience the future at different rates. In other words, the same physics that bends time may also allow a form of time travel. Once scientists began to understand how dramatically gravity could reshape time, an intriguing possibility naturally followed. If time can slow down in strong gravitational fields and also slow down when objects move at extremely high speeds, then the universe already contains mechanisms that allow different observers to move through time at different rates. In other words, the cosmos itself quietly permits a limited form of time travel. Not the dramatic journeys into the past imagined in many stories, but something equally fascinating: travel into the future. To understand this idea, imagine two travelers beginning a journey together. One remains on Earth, living a normal life under the familiar pull of our planet's gravity. The other boards a spacecraft capable of traveling at enormous speed, perhaps a significant fraction of the speed of light. The traveler inside the spacecraft experiences time normally from their own perspective. Their clock ticks steadily, their thoughts unfold naturally, and the duration of their journey feels perfectly ordinary. But because their spacecraft is moving so quickly through space, time for them passes more slowly relative to observers on Earth. If the traveler eventually returns home after what feels like a few years of personal time, they might discover that far more time has passed on Earth. Decades or even centuries could have unfolded while they were away. In this sense, the traveler has moved into the future relative to those who remained behind. This form of time travel is not speculative fantasy. It is a direct prediction of relativity. Experiments with fast-moving particles and precision clocks confirm that motion can indeed slow the passage of time relative to other observers. Gravity offers another route to a similar outcome. Imagine spending time in a region of extremely strong gravity, such as near a neutron star or close to the event horizon of a massive black hole. Because time flows more slowly in these environments, an observer living there would experience fewer seconds passing compared with someone far away from the gravitational field. If that observer later returned to a region of weaker gravity, they would find that more time had passed elsewhere in the universe than they personally experienced. Once again, the traveler would have effectively moved into the future relative to others. Of course, such journeys are not easy. The engineering challenges involved in traveling at relativistic speeds or surviving near intense gravitational fields are enormous. The energy required to accelerate a spacecraft close to the speed of light would be staggering. And the tidal forces near compact objects like neutron stars or black holes could easily destroy any ordinary structure. Yet the laws of physics themselves do not forbid such journeys. On the contrary, relativity quietly allows them. This realization leads to a remarkable conclusion. The universe is not built around a single universal timeline. Instead, it allows many possible paths through spacetime, each with its own rhythm of time. Travelers following different paths may experience different durations even if they later reunite at the same event. In a sense, the geometry of spacetime contains countless hidden routes through time. Most of these paths differ only slightly, producing differences far too small to matter in daily life. But under extreme conditions, the divergence can become enormous. This idea also reveals why relativity has had such a profound influence on science fiction. The thought that explorers could journey across the galaxy and return to a distant future on Earth is not merely imaginative storytelling. It emerges naturally from the mathematics describing spacetime. Yet relativity also places strict limits on what kinds of time travel may be possible. While traveling into the future appears to be allowed by the laws of physics, traveling into the past presents far greater challenges. The equations of general relativity contain certain exotic solutions that hint at the possibility of paths through spacetime that loop backward in time. These paths are sometimes called closed time-like curves. In theory, an object following such a path could arrive at an event in its own past. However, creating the conditions required for such paths appears to demand structures far beyond anything we know how to produce. Some theoretical proposals involve hypothetical tunnels through spacetime known as wormholes, which might connect distant regions of space and time. But these ideas require forms of matter with unusual properties that have never been observed in practical quantities. For now, backward time travel remains an open question in theoretical physics. What we know with certainty is that the universe already permits a subtler and more elegant phenomenon: the ability for different observers to experience time differently depending on their motion and gravitational environment. And when we step back and look at the universe as a whole, an even deeper realization begins to emerge. The cosmos is not governed by a single master clock. Instead, it is filled with countless clocks, each following its own path through the curved geometry of spacetime. When we step back from the details of equations and experiments, the picture that emerges from relativity is both strange and quietly beautiful. Time is not a rigid backdrop stretching across the universe like a perfectly synchronized grid. Instead, it behaves more like a landscape shaped by motion, gravity, and the paths that objects follow through spacetime. Each observer moves through that landscape along their own world line, carrying with them a personal measure of time that may differ slightly from the clocks of others. In everyday life, these differences are almost imperceptible. Two people walking side by side on Earth experience nearly identical flows of time. Their clocks remain synchronized to within tiny fractions of a second. Even when we travel across continents in airplanes or orbit the planet aboard spacecraft, the differences remain extremely small. The universe hides its deeper structure beneath the calm surface of our daily experience. But the moment we begin looking beyond our immediate surroundings, the illusion of a shared universal clock begins to fade. The deeper we explore the cosmos, the more we encounter environments where the rhythm of time diverges dramatically from what we are accustomed to on Earth. A spacecraft orbiting our planet experiences slightly different time than someone standing on the ground. A satellite drifting thousands of kilometers above the surface experiences another slightly different rate again. Farther away, on the surface of another planet with a different mass and gravity, time would tick at a subtly altered pace compared with Earth. Even the rotation of Earth introduces tiny variations. Points near the equator move faster through space than points near the poles, and this motion produces minute differences in the passage of time according to special relativity. The differences are incredibly small, but with modern atomic clocks they can be measured. Expand this perspective to the scale of the solar system and the variations continue. A clock on Mars ticks at a different pace than a clock on Earth because Mars has weaker gravity and follows a different orbit around the Sun. A spacecraft traveling toward the outer planets experiences changes in both motion and gravitational environment, each slightly reshaping its relationship to time. Beyond the solar system, the diversity becomes even greater. Stars orbiting close to the center of our galaxy experience stronger gravitational fields than those drifting in the outer regions of the Milky Way. Near the galactic core, where a supermassive black hole lurks, space-time curves more strongly and time flows a little more slowly compared with the calmer outskirts of the galaxy. On the grandest cosmic scales, the universe reveals itself as a vast mosaic of time flows. Every region carries its own subtle rhythm determined by its motion and the curvature of spacetime surrounding it. There is no single cosmic metronome keeping everything in perfect synchronization. Instead, the universe resembles a symphony of countless clocks. Some tick slightly faster, some slightly slower, each following its own path through the curved geometry of spacetime. When these clocks meet and compare their histories, their readings may differ. Yet none of them are wrong. Each clock faithfully records the passage of time along its own world line. This realization leads to one of the deepest insights of relativity. Time is local. What we call time is not a universal substance flowing uniformly everywhere. It is a measurement of change experienced along a particular path through spacetime. Two observers traveling along different paths may accumulate different amounts of time between the same events. In this sense, every object in the universe carries its own clock. The atoms vibrating in your body measure your personal passage through time. A pulsar spinning in distant space marks its own rhythm with extraordinary precision. The orbit of a planet around its star becomes another kind of cosmic clock. Even the decay of unstable particles provides a way to measure time along a specific trajectory. All of these clocks are valid within their own frames of reference. When physicists compare them, they are not discovering errors. They are uncovering the deeper geometry of spacetime itself. And once we accept that the universe contains countless different clocks rather than a single universal one, an even more profound question begins to emerge. If time depends on the path we take through spacetime, then what exactly is the nature of time itself? Does time truly flow the way we feel it does? Or is the sensation of time passing something created by our own perception as we move through the vast structure of the universe? These questions carry us beyond relativity and into one of the deepest mysteries in physics and philosophy. To explore them, we must look not only at the geometry of spacetime but also at the way the universe evolves, how entropy shapes the direction of events, and how our minds experience the sequence we call the present moment. And as we begin that exploration, the familiar idea of time as a simple flowing river may start to dissolve into something far more mysterious. By the time we arrive at the deepest questions about time, relativity has already changed our understanding in profound ways. We have seen that motion alters time. Gravity reshapes it. Different observers following different paths through spacetime accumulate different amounts of time between the same events. The universe is not governed by a single universal clock, but by countless local clocks, each measuring time along its own world line. And yet, despite everything physics has revealed, our everyday experience still insists on something very simple. Time feels like it flows. Moments seem to pass one after another in a steady procession. The present appears to slide forward continuously, turning the future into the past. We remember yesterday but not tomorrow. We feel ourselves moving through time in a single direction. This sensation is so deeply woven into our lives that it seems almost impossible to question. But when physicists look at the fundamental equations that describe nature, something surprising appears. Most of the laws of physics do not actually distinguish between past and future. If you were shown a film of many physical processes, a pair of billiard balls colliding, a planet orbiting a star, or light reflecting between mirrors, and the film were played backward, the motion would still obey the same equations. The mathematical rules governing these systems work almost perfectly whether time moves forward or backward. At the deepest level, the laws themselves do not seem to care about the direction of time. So where does the arrow of time come from? Why do we experience a clear distinction between past and future? One of the most important clues lies in a concept known as entropy. Entropy is often described as a measure of disorder, but a more precise way to think of it is as a measure of the number of possible microscopic arrangements that correspond to a particular state of a system. A tidy deck of cards arranged in perfect order represents a very specific arrangement. A shuffled deck represents an enormous number of possible arrangements. Because there are far more disordered configurations than ordered ones, systems naturally tend to evolve towards states with higher entropy. This tendency is expressed in the second law of thermodynamics, which tells us that the entropy of an isolated system tends to increase over time. We see this principle everywhere in daily life. Ice melts into water, Cream spreads through coffee. A neatly arranged room gradually becomes messy unless effort is spent maintaining order. These processes move naturally from lower entropy states toward higher entropy states. This increase of entropy provides a physical explanation for the direction we associate with time. We remember the past because it had lower entropy than the present. The future appears open because there are countless possible higher entropy states into which the universe can evolve. In this way, the arrow of time may emerge not from the fundamental laws themselves, but from the statistical behavior of large numbers of particles. But relativity introduces an additional layer of complexity to this picture. According to Einstein's description of spacetime, every event in the universe occupies a fixed location within a four-dimensional structure. Just as a mountain exists at a particular place within a landscape, an event exists at a particular point in spacetime. From this perspective, the past does not disappear and the future does not yet come into existence. Instead, all events, past, present, and future, may be equally part of the spacetime structure. This idea is often called the block universe. In the block universe view, time does not flow in the way we intuitively imagine. The entire history of the universe exists as a vast geometric structure. Our experience of moving from moment to moment may arise because our consciousness travels along our world line through this structure, encountering events sequentially. In other words, the flow of time might not be a property of the universe itself. It might instead be a feature of how conscious beings experience reality. This idea can feel unsettling because it challenges the familiar sense that the present moment is uniquely real. In relativity, there is no single universal now shared across the cosmos. Different observers moving relative to one another may disagree about which events are happening at the same time. The present becomes something local, tied to each observer's path through spacetime. And once we begin to think about time this way, the universe starts to look less like a river carrying everything forward and more like an immense landscape of moments, quietly existing within the deep geometry of spacetime. If the universe truly resembles a vast block of spacetime where every event already occupies its place, then the familiar feeling of time flowing from past to future may not be a fundamental feature of reality at all. Instead, it may arise from the way conscious beings like us experience sequences of events. Our minds gather information from our surroundings, arrange it into memories, and construct a continuous story that moves from what has happened toward what will happen next. This narrative experience is deeply connected to how our brains process information. At any given moment, our senses collect signals from the environment. Light entering our eyes, sounds reaching our ears, pressure against our skin. The brain does not treat these signals as isolated fragments. It weaves them together into a coherent perception of the present moment. But this process takes time. The brain must integrate information over short intervals in order to create the smooth, flowing experience we recognize as consciousness. Because of this integration, our awareness is always slightly delayed. The present moment we perceive is actually a carefully assembled interpretation of events that have already occurred fractions of a second earlier. Our brains then compare this incoming information with stored memories, constantly updating the story we experience as reality. In this sense, the flow of time may be closely linked to the way memory works. We remember past events because physical traces of them exist in our brains and in the world around us. Photographs, written records, and the marks left by physical processes all carry information about earlier states of the universe. The future, by contrast, has not yet left such traces. It exists only as possibilities. Entropy plays an important role here as well. Because entropy tends to increase, physical systems naturally evolve from more ordered states toward more disordered ones. This progression leaves behind records of earlier conditions. When a glass shatters on the floor, the scattered pieces provide clear evidence that the glass was once intact. But the reverse situation, a pile of fragments spontaneously assembling into a perfect glass, would not produce such records. Our memories and the physical records around us are therefore aligned with the thermodynamic arrow of time. They point toward the past, not toward the future. This alignment reinforces our experience of time having a clear direction. Yet when physicists examine the fundamental equations governing the motion of particles, they still find that these equations themselves do not prefer one direction of time over the other. The arrow of time emerges not from the basic laws alone, but from the particular conditions under which our universe began. Evidence from cosmology suggests that the early universe existed in an extremely low entropy state shortly after the Big Bang. In other words, the universe started out remarkably ordered. As it expanded and evolved, entropy gradually increased, producing the thermodynamic arrow of time we observe today. This raises a fascinating possibility. The direction we associate with time may ultimately trace back to the special conditions present at the birth of the universe. If the universe had begun in a high-entropy state instead, the distinction between past and future might be far less noticeable. Relativity adds another subtle twist to this story. Because simultaneity depends on the observer's motion, there is no universal slice of spacetime that can be identified as the present for the entire cosmos. Two observers moving relative to one another may disagree about which distant events are occurring right now. What one observer calls the present might lie in another observer's past or future. This means the present moment is not a global property of the universe. It is something local, defined by the observer's path through spacetime. Each world line carries its own sequence of events, and along that path the observer experiences a personal flow of time. From this perspective, our sense of moving through time may simply reflect our movement along our world line within the larger spacetime structure. Just as a traveler walking through a landscape encounters different locations one after another, we encounter different events along our trajectory through spacetime. But the landscape itself does not move. All the locations already exist. If this view is correct, then the universe may contain an immense tapestry of moments stretching across space and time. Every event, every birth of a star, every orbit of a planet, every human thought, occupies its own position within that structure. Our experience of time flowing may arise because consciousness reveals those moments to us one by one as we move along our path. And this realization leads us toward one final reflection about our place within the cosmic fabric of spacetime. When we begin to see time through the lens of relativity and thermodynamics, our familiar picture of reality quietly transforms. Instead of imagining the universe as a stage where the present moment advances like a moving spotlight, we begin to see something closer to an immense cosmic structure. Within that structure, every event occupies its own place. The birth of stars, the formation of galaxies, the quiet passing of human lives, and even the thoughts forming in your mind at this moment all belong to different points along the vast fabric of spacetime. From this perspective, the universe resembles an enormous map rather than a flowing river. The past is not something that has vanished, nor is the future something that must still be created. Both may already exist as regions within the spacetime landscape. Our experience of moving forward through time could simply reflect our journey through this map along a particular path. Physicists sometimes describe this path as a world line. Every object traces one through spacetime. The Earth follows a gentle spiral as it orbits the Sun while the Sun moves through the galaxy. Photons travel along paths that carry them across billions of years of cosmic history. Even you, sitting wherever you are right now, are tracing a quiet world line through the universe. At each point along that path, your brain constructs the experience we call the present moment. And yet something remarkable happens when we consider this idea more deeply. If the block universe picture is correct, then the moments we call past and future are simply different locations within spacetime. They do not flow toward us any more than distant cities flow toward a traveler walking across a landscape. Instead, we move. Our awareness advances step by step along our world line, revealing events sequentially. But the landscape itself remains still. Yet, in the geometry of spacetime, it may simply be that we are traveling. Each observer follows a unique path through the cosmic landscape. Two travelers moving differently through spacetime may experience different sequences of events or accumulate different amounts of time between meetings. Relativity has shown that even the concept of simultaneous events can depend on the observer's motion. What seems like the present moment to one observer might lie slightly in the future or the past for another. In this way, the universe contains not one shared present but countless overlapping perspectives on time. Every star system, every galaxy, every observer carries its own local rhythm within the larger structure of spacetime. This diversity does not create chaos. Instead, it forms a beautifully consistent geometric order described by the equations of relativity. Those equations quietly coordinate the relationships between all these clocks, ensuring that the universe remains internally coherent even though time flows differently in different places. It is a subtle harmony. The same principles that guide the orbit of planets also determine the ticking of clocks aboard satellites. The curvature of spacetime that bends the path of starlight also stretches the duration of seconds near massive objects. Space and time are inseparable partners in shaping the cosmos. And once we understand that, the final mystery becomes less about measuring time and more about reflecting on what it means to exist within such a universe. Because if time is part of the geometry of reality itself, then every moment we experience is not just passing away. It is part of the structure of the cosmos. As our journey through the mystery of time begins to slow, It is worth pausing for a moment to reflect on how extraordinary this picture of the universe truly is. For most of human history, time seemed like the simplest thing imaginable. It was the steady ticking of clocks, the rhythm of day and night, the quiet march of years. It appeared uniform, predictable, and universal. No matter where you stood on Earth, time seemed to flow the same way for everyone. But the deeper we looked into the structure of the cosmos, the more that simple picture began to dissolve. We discovered that time stretches when objects move quickly through space. We learned that gravity bends the pace of seconds, slowing clocks in deeper gravitational wells. We found that the universe is not synchronized by a single master clock, but filled instead with countless clocks, each following its own path through space-time. Even the feeling that time flows steadily forward may not belong to the universe itself. It may arise from the way conscious beings like us experience sequences of events while traveling along our world lines. Our memories record the traces of lower entropy states, while the future unfolds toward greater complexity and disorder. In this way, the arrow of time emerges from the deep statistical behavior of the universe. Yet despite all of these discoveries, something about time remains deeply mysterious. Physics can describe how time behaves with extraordinary precision. The equations of relativity allow us to predict how clocks will differ depending on motion and gravity. Cosmology traces the evolution of the universe from its earliest moments to the vast cosmic structures we observe today. Thermodynamics explains why events unfold in a particular direction. But none of these explanations fully answers the most profound question of all. Why does time exist at all? Why does the universe contain this dimension through which events are ordered? Why do we experience moments in sequence rather than all at once? These questions sit quietly at the boundary between physics and philosophy, where even the most powerful theories cannot yet provide a complete answer. And perhaps that mystery is part of what makes time so fascinating. Every moment you experience is part of an immense cosmic structure stretching across billions of years and billions of galaxies. Your life traces a delicate thread through space-time, just as every star and every planet traces its own path through the same vast fabric. Somewhere in the universe, near the edge of a black hole, time may be passing far more slowly than it is for you right now. In other regions, clocks may be running slightly faster as galaxies drift through weaker gravitational fields. Across the cosmos, countless observers experience their own rhythms of time, each one valid within its own frame of reference. Yet all of these moments belong to the same universe. The same space-time geometry holds them together, linking every world line into a single interconnected structure. And within that immense structure, you are quietly traveling through time right now. Even if you feel perfectly still, your world line continues forward through the space-time landscape. Each heartbeat marks another step along your path. Each breath carries you slightly farther into the future. But perhaps the most comforting thought is this: if time is part of the geometry of the universe, then every moment you experience becomes part of that geometry as well. The conversations you have, the memories you create, the quiet evenings you spend beneath the stars, all of them occupy their own place in the vast tapestry of space-time. They do not simply vanish. They become part of the structure of the cosmos itself. So tonight, as the seconds pass quietly and the universe continues its silent expansion, you are not merely watching time move forward. You are participating in one of the deepest processes in nature, the unfolding journey of a conscious mind through the extraordinary landscape of spacetime. And somewhere out there among the stars, countless other clocks continue to tick in their own quiet rhythms, each marking another gentle step through the beautiful mystery we call time. For many people, this idea feels unsettling at first. It challenges the deeply rooted intuition that the future does not yet exist and that the past has already disappeared. In the block universe view, those distinctions are not fundamental features of reality. They arise from our limited perspective as observers embedded within spacetime. Yet there is also something quietly beautiful about this picture. If every moment exists within the spacetime structure, then the universe contains a vast tapestry of events stretching across unimaginable distances and durations. Every moment of joy, every discovery, every quiet evening beneath the stars is part of that tapestry. Nothing is truly erased. It simply occupies its own place in the geometry of the cosmos. Relativity also reminds us that there is no single universal now shared across the entire universe. Because observers moving differently through spacetime experience time differently, the concept of the present moment becomes relative. Two observers far apart in space, moving relative to one another, may disagree about which distant events are happening at the same time. In this way, the universe contains not just many clocks, but many perspectives on time itself. Each observer experiences their own sequence of moments, their own flow of time shaped by their motion and their position in the gravitational landscape. No single viewpoint is privileged above the others. This realization can change the way we think about our place in the cosmos. We often imagine ourselves as small beings carried helplessly forward by time. But relativity suggests something slightly different. Each of us is following a unique path through spacetime, tracing our own world line across the cosmic landscape. Our experiences unfold along that path, one moment after another. And while the universe itself may not contain a single flowing river of time, it does contain countless journeys through time. Every star, every planet, every living creature is traveling along its own trajectory within the immense geometry of spacetime. The deeper we explore this idea, the more we begin to sense that time is not just a physical parameter used by scientists to measure change. It is part of the architecture of the universe itself. And understanding that architecture brings us closer to one final reflection about the quiet mystery of time and our place within it. When we pause and look at the universe through this broader lens, time begins to appear less like a force carrying us forward and more like a dimension in which existence unfolds. Just as we move through space from one place to another, we also move through time along our world lines. The difference is that while we can freely change direction in space, our motion through time seems to follow a single consistent direction. Yet even this sense of direction may not be as fundamental as it first appears. As we explored earlier, the arrow of time seems closely linked to entropy, the tendency of physical systems to evolve toward greater numbers of possible configurations. The universe began in a remarkably ordered state, and since that moment entropy has been gradually increasing. This gradual unfolding of disorder provides the direction we perceive as the forward flow of time. But within the deeper framework of spacetime, every event remains part of the cosmic structure. The Big Bang, the formation of galaxies, the birth of our sun, and the moment you are experiencing right now all occupy positions within the same vast four-dimensional tapestry. The difference is simply where each event lies along the dimension we call time. To picture this, imagine the entire history of the universe represented as an immense landscape stretching across both space and time. Somewhere within that landscape lies the formation of the first atoms. Farther along lies the ignition of the first stars. Still farther along appear the spiral arms of galaxies and the quiet emergence of planets orbiting their suns. And along one tiny thread within that enormous structure lies the history of Earth. On that thread we find the formation of oceans, the slow evolution of life, the rise of civilizations, and the countless small moments that make up human experience. Every conversation, every sunrise, every quiet evening beneath the night sky becomes another point along that path. From the outside, the entire thread exists at once. But from within it, we encounter those moments sequentially. Our awareness moves from one event to the next, assembling a continuous narrative that we call the present. Memory allows us to look backward along the thread toward earlier moments, while imagination allows us to anticipate the possibilities that lie ahead. This combination of perception, memory, and expectation gives rise to the sensation that time itself is flowing. Yet, in the geometry of spacetime, it may simply be that we are traveling. Each observer follows a unique path through the cosmic landscape. Two travelers moving differently through spacetime may experience different sequences of events or accumulate different amounts of time between meetings. Relativity has shown that even the concept of simultaneous events can depend on the observer's motion. What seems like the present moment to one observer might lie slightly in the future or the past for another. In this way, the universe contains not one shared present but countless overlapping perspectives on time. Every star system, every galaxy, every observer carries its own local rhythm within the larger structure of spacetime. This diversity does not create chaos. Instead, it forms a beautifully consistent geometric order described by the equations of relativity. Those equations quietly coordinate the relationships between all these clocks, ensuring that the universe remains internally coherent even though time flows differently in different places. It is a subtle harmony. The same principles that guide the orbit of planets also determine the ticking of clocks aboard satellites. The curvature of spacetime that bends the path of starlight also stretches the duration of seconds near massive objects. Space and time are inseparable partners in shaping the cosmos. And once we understand that, the final mystery becomes less about measuring time and more about reflecting on what it means to exist within such a universe. Because if time is part of the geometry of reality itself, then every moment we experience is not just passing away. It is part of the structure of the cosmos. As our journey through the mystery of time begins to slow, It is worth pausing for a moment to reflect on how extraordinary this picture of the universe truly is. For most of human history, time seemed like the simplest thing imaginable. It was the steady ticking of clocks, the rhythm of day and night, the quiet march of years. It appeared uniform, predictable, and universal. No matter where you stood on Earth, time seemed to flow the same way for everyone. But the deeper we looked into the structure of the cosmos, the more that simple picture began to dissolve. We discovered that time stretches when objects move quickly through space. We learned that gravity bends the pace of seconds, slowing clocks in deeper gravitational wells. We found that the universe is not synchronized by a single master clock, but filled instead with countless clocks, each following its own path through space-time. Even the feeling that time flows steadily forward may not belong to the universe itself. It may arise from the way conscious beings like us experience sequences of events while traveling along our world lines. Our memories record the traces of lower entropy states, while the future unfolds toward greater complexity and disorder. In this way, the arrow of time emerges from the deep statistical behavior of the universe. Yet despite all of these discoveries, something about time remains deeply mysterious. Physics can describe how time behaves with extraordinary precision. The equations of relativity allow us to predict how clocks will differ depending on motion and gravity. Cosmology traces the evolution of the universe from its earliest moments to the vast cosmic structures we observe today. Thermodynamics explains why events unfold in a particular direction. But none of these explanations fully answers the most profound question of all. Why does time exist at all? Why does the universe contain this dimension through which events are ordered? Why do we experience moments in sequence rather than all at once? These questions sit quietly at the boundary between physics and philosophy, where even the most powerful theories cannot yet provide a complete answer. And perhaps that mystery is part of what makes time so fascinating. Every moment you experience is part of an immense cosmic structure stretching across billions of years and billions of galaxies. Your life traces a delicate thread through space-time, just as every star and every planet traces its own path through the same vast fabric. Somewhere in the universe, near the edge of a black hole, time may be passing far more slowly than it is for you right now. In other regions, clocks may be running slightly faster as galaxies drift through weaker gravitational fields. Across the cosmos, countless observers experience their own rhythms of time, each one valid within its own frame of reference. Yet all of these moments belong to the same universe. The same space-time geometry holds them together, linking every world line into a single interconnected structure. And within that immense structure, you are quietly traveling through time right now. Even if you feel perfectly still, your world line continues forward through the space-time landscape. Each heartbeat marks another step along your path. Each breath carries you slightly farther into the future. But perhaps the most comforting thought is this: if time is part of the geometry of the universe, then every moment you experience becomes part of that geometry as well. The conversations you have, the memories you create, the quiet evenings you spend beneath the stars, all of them occupy their own place in the vast tapestry of space-time. They do not simply vanish. They become part of the structure of the cosmos itself. So tonight, as the seconds pass quietly and the universe continues its silent expansion, you are not merely watching time move forward. You are participating in one of the deepest processes in nature, the unfolding journey of a conscious mind through the extraordinary landscape of spacetime. And somewhere out there among the stars, countless other clocks continue to tick in their own quiet rhythms, each marking another gentle step through the beautiful mystery we call time.